Welcome to the kinematics of rigid body motion. Today we are going to discuss infinitesimal rotations. Throughout the discussion so far, we have associated various matrices with the description of a rigid body's orientation. However, the number of matrix elements has always been larger than the number of independent degrees of freedom, leading to various supplementary conditions carried along in the description. We now know that any orientation can be established by a single rotation about a suitable axis. We want to associate a vector defined by three independent quantities with a finite displacement of a rigid body about a fixed point. We could assign the direction of the vector to be given by the axis of rotation and its magnitude as a function of the rotation angle. We can then assume that the vectors A and B are associated with the transformation matrices A and B. We then know that vector addition is commutative. However, we also know that matrix multiplication does not commute, and this fact leads to the conclusion that vector addition should not commute, which is in contradiction with our previous statement. Thus, the conclusion is that the sum of finite rotations depends on their order. However, if we were to define an infinitesimal rotation by the linear transformation here, where the epsilon coefficients vanish in second order, then such a transformation can be written compactly as here, which is equivalent with this expression for the three components, or in matrix form, it is equivalent with the transformation here. So the transformation of vector x to x prime through the matrix given by the sum between the identity matrix plus the matrix of transformation epsilon containing these coefficients. And we see that if we were to apply two such transformations in succession, then if we carry the matrix multiplications out and keep in mind that these coefficients vanish in second order, then we see that since matrix addition is commutative, the order in which these two transformations are applied leads to the same result. So infinitesimal rotations can be represented by vectors. The infinitesimal version of the general transformation matrix 446 is given here, and we will see shortly that to this there can correspond a vector having these components, and it will make sense right away why we would write it in this specific form. First of all, observe that the particular matrix product here is equivalent with the identity matrix, so therefore the inverse of the matrix A defined to be 1 plus epsilon is simply 1 minus epsilon. And since this is an orthogonal matrix, the inverse is equal with the transpose, so the conclusion is that the transpose of epsilon is minus epsilon. Thus, the matrix epsilon has only three distinct elements and is antisymmetric, having the general expression here. And you can see that if we write it in this particular form, then the three components of the vector omega are in fact those given here, assuming that these components correspond to the x, y, and z axes. So these three independent these three numbers, delta omega I, are three independent quantities specifying a rotation and the three components of a particular kind of vector. Notice that the transformation 464 can be written in the form here, so the difference between the rotated and the original vector is equal with the application of the matrix epsilon to the original vector, and in component form, the matrix has this equation is constituted of the three scalar equations given here. So the left-hand side is given by dx1, 2, and 3, and using this form of epsilon, the right-hand side is given by the differences here. It is important to stress that d omega is not the differential of a specific vector, but rather it is a vector of a differential magnitude, as no single vector can represent a finite rotation due to the contradiction involved, as we've seen earlier. And in any case, observe that the set of equations of 471 can be written compactly as here. So an infinitesimal element of the rotated vector is given by the cross product between an infinitesimal element of the original vector in vector product with the vector d omega. Now, since the radius is a vector, it transforms under an orthogonal matrix B as given by the rule here. So if d omega were truly a vector, then it should also transform under an orthogonal matrix B in the same way. And in order to investigate this, we will first define the matrix epsilon prime by the similarity transformation of epsilon under B. And as antisymmetry is preserved under similarity transformation, the non-vanishing elements will be determined by the three components d omega prime. So to begin with, we need to put the following things together. The elements of the matrix epsilon are given by the expression here. So this is just the Levi-Civita totally antisymmetric tensor multiplying the component d omega j. We have defined epsilon prime as the similarity transformation of epsilon under the orthogonal matrix B. So these two equalities hold. And then in component form, or written for a particular element of epsilon prime, the above expression is translated in this way. And at the same time, since under similarity transformation the matrix must remain antisymmetric, we know that the components of epsilon prime must be of this form. So then if we put all of these things together, we obtain the result here. Now, for a matrix that is of a dimensions 3 by 3, and if we assume that the permutation of indices written here is cyclic, the general definition of a determinant is the one here. Or we could define it in a way which does not require any sort of restriction on the sequence of indices by using the expression here. Now, if this result is applied to the matrix B and to the determinant of the matrix B, and we remember that B is orthogonal and proper, then we immediately obtain, so by writing this expression for the determinant of B and multiplying with B, we obtain the result here. And then if we put result 5 together with result 8, we immediately obtain the lengthy expression here, which can be contracted by remembering that B is orthogonal, and it leads to this identity, which features the same Levi-Civita symbol on both sides. So we can write simply the coefficient multiplying the symbol to obtain the transformation law here. Observe that if B is orthogonal and proper, we see that the components of d omega prime transform exactly as a vector under such a transformation. However, if B is orthogonal but improper, there is a sign carried over here. So there is a subtle difference between the way a vector would transform and orthogonally and the way this object transforms. Furthermore, if we go back to the formula for finite rotations and we take its infinitesimal limit, the result we immediately obtain is the one here. And then if we put equations for 72 and this one together, we obtain that the object d omega is equal with has its components equal with the components of the axis of rotation multiplied by the differential of the rotation angle. We can also derive the result for 75 directly from a simple geometric argument. The infinitesimal transformation we are discussing is the rotation of a vector r going clockwise for an angle d phi about the axis of rotation. Then the distance swept by the endpoint of the vector during this rotation is simply the one given here in spherical polar coordinates, and its orientation is perpendicular both to the radius vector itself and the vector d omega given by the product here. And its sense follows from the right-handed screw rule, as the vector r is turned into the omega, thus leading directly to 475. The transformation law of 472 defines what are known as polar vectors, and under an inversion of the coordinate axis having the elements here, all of the components of a polar vector change sign. However, for what is known as an axial vector or a pseudovector, the components do not change sign, and pseudovectors are defined as the cross product of two vectors having the components given here. And the components of these two vectors, let's see, d and f, change sign under an inversion, but what will follow is that the components of their cross product, the pseudovector v star, do not. Examples of physical quantities that are pseudovectors are the angular momentum L or the magnetic field induction B. Such quantities will transform under equation 474. Axial and polar vectors are indistinguishable under proper orthogonal transformations, but they behave differently under inversions of the coordinate axes. And now if we define a parity operator B, the four types of quantities that are of importance in classical mechanics behave in the following way. Scalars are invariant to the action of the parity operator. They do not change in any way. Vectors change sign under a parity transformation, which so parity is simply going from a right-handed to a left-handed coordinate system, and in this case the vectors change sign. Pseudovectors are also invariant to a parity transformation, and the quantity given by the dot product between a vector and a pseudovector also changes sign, and this is known as a pseudoscalar. From the passive perspective, an inversion changes the sign of the coordinate axis and as such the signs of the components of a polar vector, leading to its change in sign. In the case of axial vectors, the quantities carry their handedness convention along as per the definition of the cross product in equation 477. Under inversion, a right-handed system becomes left-handed, and the cyclic requirement of 477 demands a similar change from right-handed to left-handed screw convention. Thus, even in the passive interpretation, there is an actual change in the direction of the cross product upon inversion. As in 475, both r and dr are polar vectors, and then therefore the omega must be axial vectors. The inversion of the coordinates corresponds to an inversion from right-handed to left-handed screw rule, defining the sense of the axis of rotation. Another way to write the components of a pseudovector is for the use of the Levi-Civita tensor as shown here. And so far we have mainly been interested in the rotation of the coordinate systems, but many times the rotation of a physical system is also important. Furthermore, we have established the connection between invariance to rotation and angular momentum conservation. In such situations, it is necessary to consider the behavior of vectors rotated through the counterclockwise sense. And to this end, and for completeness, are given here the rotation formula for a counterclockwise rotation, both in its finite and infinitesimal expressions. And to such a counterclockwise rotation of a vector, there would correspond a matrix epsilon given by the structure here, which is equivalent with the matrix n having these components multiplied with the infinitesimal rotation angle. The expression 466 we wrote previously is entirely equivalent with the result here, where we would say that the rate of change of r with respect to the rotation angle is given by minus the matrix n multiplying the original vector, and thus epsilon can be represented in the form here with the free matrices m1 and 2 and 3 having these elements, and they are known as the infinitesimal rotation generators, having this property. So any two of them put together in this structure, which is known as a commutator, result in the third matrix with a coefficient given by the permutation symbol here. So, and this commutator is known as a Lie bracket, and it defines the Lie algebra of the rotation group parametrized in terms of the rotation angle. In summary, we found a quantity with three components that can describe an infinitesimal orthogonal transformation, and have deduced that it is a pseudovector. We have discussed the differences between scalars, vectors, pseudovectors, and pseudoscalars, and have represented the matrix of infinitesimal rotations in terms of the infinitesimal rotation generators and their Lie algebra. In the following, we are going to discuss the rate of change of a vector. So, with all that being said, I want to thank you very much for watching. I hope you found the video worth your time, and I will catch you later. Goodbye.